Hi, I'm Jacob. In this video, I want to give you a quick overview of what ground and reference mean with regard to electrophysiology, mostly extracellular electrophysiology, but really it's the same even when we talk about something like an EEG system or an EMG recording. You might have seen on the EIB, electrode interface board, or somewhere on your EFIS system that there's a ground connection, but there's also this ref connection. This is what this looks like on our shuttle drive, EIB. This is what this looks like on a head stage. So there's a ground input and a ref input. So what are these good for? At the most basic level, when you think about the amplifier that sits on the head stage, and this is an instrumentation amplifier in the broadest sense of the term, you have a positive and a negative input. And then you have the ground that connects to whatever reference level you're using. So this could be the laptop that you plug into it, really whatever is the ground level. So what this means is you have an extremely high input impedance here and here, and you have an extremely low one down here. If we have a weak signal from a tetrode or something like that we can conceptualize as having a very high output impedance, then we can still record from that just fine because we are not dropping any voltage across this resistor because there is no current flowing in and out of here. So the same goes for our reference signal, of course. So if we have some reference electrode that also has a relatively high impedance, then we can still record that signal. Whereas our ground input is able to sink or source as much current as is necessary. So as we'll see, the ground input is really good at one thing, and that is bringing whatever it is connected to close to 0 volt. The reference signal is subtracted from the tetrode signals, in theory, in an exact one-to-one fashion in an instrumentation amplifier, as you've seen in the other videos, with exactly matched input impedance, which gives us very good common mode rejection. Now, in reality, the situation is a little bit different often. So here is the spec sheet from the Intel RHD chips that we're using in the OpenEFA systems, and like a lot of other systems are using those. So when we zoom into it a little bit here, we can see that the reference input is shared among all the channels. And then you have the electrode inputs going into the differential amplifiers here. In practice, the input impedances are not perfectly matched, but it's certainly a higher input impedance than the ground input. So what does this mean in practice? So let's imagine you have a mouse that you're recording from, and you have some tetrode in there, and then you have your amplifier. The amplifier is connected to a computer. You would first have the tetrode connected to the input of the amplifier. And so now you need to have some reference signal, right? Because the animal sits in some environment in which it is subjected to a lot of common mode noise. So you could imagine that you have, for instance, a lot of 60 hertz noise floating around everywhere. So that noise is all over the animal. And to get rid of that, what you want to do is you want to have a reference electrode somewhere on the animal that only picks up that 60 hertz noise or motion artifacts, whatever other noise you might have. But then you have your tetrode that, in addition to that noise, also picks up your spikes of interest. And now we have a reference electrode, let's say a screw somewhere. You're probably familiar with the term ground screw. So now that could connect to the other input. And now, because of the nice common mode rejection that we talked about in this instrumentation amplifier here, the output of the whole system ought to be just the spikes with none of the noise. In this situation, we have completely ignored the ground, and we have just said, okay, let's use the common mode rejection properties of the instrumentation amplifier. Just label this ref, this is our reference signal here, and then our tetrode signal here, tetrode. The first problem that happens here is that the animal, if it's sitting in a plastic box or something like that, could very easily be at, let's say, 1,000 volt or something like that, because it's just picking up static electricity from the environment. That is 1,000 volt relative to whatever your computer is plugged into. That's the first problem. And so in the lecture on instrumentation amplifiers, we'll get into why an instrumentation amplifier, even though it has very good common mode rejection, cannot very easily deal with potential difference, right? At some point in here, the inputs need to be referenced to the outputs, which are ground referenced, so we can't have an arbitrary input range on our amplifier. In fact, most amplifiers have a relatively small input range, so if you had something like that, you would saturate the amplifier like crazy. So that's the first reason why this might not be a good situation. The other consideration is that the ground level is often static. In almost all cases, practically speaking, you are better off if you start getting the animal that you're recording from to ground level. So you want a situation where the animal is somewhat close to ground, and now you can record your spikes. To do that, practically speaking, what most people do is that they just take the ground and they connect it to the reference. And so now what happens is that the ground screw, or the reference screw, whatever you want to call it, so now it makes sense why it might be called ground screw, is also pulling the entire animal to ground, whatever that might be, even if it's going up and down. Imagine a very bad scenario in which your ground level is fluctuating relative to the rest of the room. Then the ground screw would be charging and discharging the animal, let's say at 60 hertz or something, hopefully taking the entire animal up and down to that level. And so now, because the reference input to your instrumentation amplifier is also tied to ground, you're basically just bringing the entire animal to the level of your reference input. So now you can also understand why it's not a big problem that on the Intel chip, for instance, the input impedances aren't perfectly matched, because we're not really making that much use of them, because now the entire animal for our purposes is sitting at 0 volts. So now our tetrad signal is just relative to that, and we're happy. So that's how most recordings are done. And practically what that looks like is that most people on the EIB just connect them together and call it a day. So there's one more interesting and practically important thing when it comes to grounding animals or ourselves in the case of EMG, EEG, what have you. And that is we typically also put ourselves or animals in Faraday cages. And as we talked about, the input impedance of the inverting input of our amplifier doesn't matter much because it's basically being fed by the infinitely low output impedance that is ground, right? Ground can source or sink as much current as is needed. And so now let's imagine that there's a room or a cage or something like that. And now the room or cage could be at a different potential. So let's imagine, as we talked about before, there's some variation in the ground that our computer is on. This could be from the computer's power supply. It doesn't really matter. But there's a slightly different voltage fluctuation present in the room. This could simply be that the cage that you're doing your recording in is not perfectly grounded, that it has its own capacitance or something along that line. So now the animal is sitting in an environment in which the charges that surround it are constantly flipping back and forth. So this is not quite the same thing as shielding the animal from environmental fields, which we also do. This is a separate topic, right? So the interior field that is in this box now, because it's a Faraday cage, is homogeneous. So there is no problem with charging part of the animal differently from another part of the animal. But instead here, we're just talking about the case that the electrical potential of the cage is not the same as the electrical potential of the animal. So now what you're asking your ground screw to do is to bring the animal up and down to the ground level that is dictated by the ground of your computer. So that's this path here. And you're hoping that that's enough to bring the entire animal to that level. But at the same time, you have some other voltage from the outside, and the animal is either resistively or at least capacitively coupled to the environment. And so that's now also trying to bring the animal to that level. So the animal is a bit of a little voltage divider. You can think about it like that. So depending on how good the impedance of your ground screw is, so you want it to be as low as possible, the ground screw might very well win. So you might get a good recording that way. But in a lot of cases, you also have the problem that the tether going down to the animal is a bit of a resistor. Now, the impedance of the ground screw going to ground that you're trying to bring the animal to ground level with is not low enough. A simple solution to that is to just take the entire cage and ground it. And so now everything is more or less at the same level and the ground screw can do its job more easily. So here, just to give us another way of thinking about it and a bit of intuition, I built the exact same situation in the circuit simulator. This guy here should be familiar to you by now. This is just our instrumentation amplifier. And previously we had considered a situation like this. On the left side, you have a common mode noise, and then we add to that our spike signal here, and we're using instrumentation amplifier to separate out the spikes that, despite being small, are only present on one of the inputs and not on the reference input. So this would be the reference input up here. This would be our channels, and then wherever we have a ground symbol would be our ground. Down here, I put a model of a mouse in a cage, and this is basically just a a bunch of resistors stuck together. Obviously, that's not what a mouse looks like, but electrically, for our purposes, it's a sufficient approximation when we forget all the capacitive and inductive components, let alone any of the biology. And then the mouse is coupled to the cage with some simple capacitor here. So I'm going to move my neuron down here into the mouse, and I'm going to apply the noise to the cage. And now we're going to connect our tetrode to the mouse. And so we could, for instance, begin by just grounding the reference and see what happens. This obviously doesn't work well, and all we're seeing is some saturating noise signal because the animal is being pulled up and down by the environmental noise through the cage, and we're not subtracting that out. So now let's do a more realistic example, and let's see if we can bring our mouse to the ground level of our system. Now, mind you, here this ground level is perfectly zero. That could be your computer ground, might be a little bit different from the ground on a different outlet in your room, or from the ground that you would get if you went outside, dug a hole, and buried a long wire. So let's connect ground and ref together. So now we've connected a ground screw somewhere on the animal, not extremely close to the tetrode, but close enough so that our ground reference input can bring the animal to our ground level, and we can get some recording. Though you see there's still a lot of noise here. So this is a fairly realistic situation that you might be familiar with. So now let's go one step further and make it a little bit more realistic. And instead of having a ground screw and a tether going to the recording system with an arbitrarily low impedance, let's imagine we have maybe a ground screw that's not perfect, or just a very long tether here that has some resistance. And so let's see what happens now. And you can see the situation became much worse because now our impedance of the ground screw has gotten high enough where it cannot force the animal to ground level, and instead the animal is being pushed up and down by the environmental noise. This could happen just because the cable is long. This could happen because your ground screw is not good. This could happen because your ground screw is too far away to where you're doing your recording. One thing we can do in that situation is, instead of trying to bring the mouse to the correct level more aggressively, we can try to reduce the impact of the environmental fluctuation by making the cage closer to ground level. To simulate this, I'm taking a resistor and I'm just grounding the Faraday cage here. So mind you, this is the same ground as this. So in real life, this would be the alligator clip with the long wire that goes from your acquisition system's ground input to the tinfoil on your Faraday cage. So let's see what impact that has on our recording. You can see that because of the voltage divider that I put here, so basically I have not assumed that I've done a perfect job at getting the environment to ground level. It has made our recording much nicer because now our ground screw doesn't have to work quite as hard in bringing the animal to the correct voltage level. So what are situations when you might not want to do this? So you could imagine that you're in a situation where you know that there's a lot of noise, and that even if you have a scheme where you are grounding the animal to your reference level through something like a skull screw somewhere, so now you could have a dedicated ground screw that is just there to bring the animal to ground level. And now you could have a separate reference electrode, a tetrode that you put into white matter. Some people use a tetrode that has been partially de-insulated to provide a lower impedance reference. And you put that somewhere close to where you're recording, but not all the way there. So now you get the ability to get rid of most of the voltage fluctuations of the animals with your ground screw, but you're additionally taking advantage of the fact that you can have another local reference that you subtract out from the signal of interest on your tetrodes. I'm saying tetrodes, but really this applies to any kind of electrode. For this to be maximally efficient, you might want to use a truly bipolar instrumentation amplifier where the input impedances of the positive and negative inputs are met. So in the case of Intel, there is a chip that they make, has half the number of channels, but avoids splitting the reference signal to give you a matched input impedance, for instance. You need to know what your signal is, right? So if you do this and you want to record an LFP signal, the signal that is present on your reference electrode is going to be contaminating, or it's going to be showing up in an inverted manner in all your other signals. This is the kind of thing where, for instance, if you do EEG, people pay a lot of attention to which electrodes are grounded and which electrodes are used as reference for what, because that really changes the signal that you get out of that. So I hope this made sense, and next time you see the ground and ref inputs on your head stages, it makes a little bit more sense what they're there for. And as always, if you have questions, please ask them in our forums.